Hi, this is Kanchana Murthy, working as Assistant Professor in SNS College of Technology. So, in this video, we are going to see about process scheduling and synchronization. So, many students ask, why do we study problem about bakers or barbers in the computer class? The reason is that these are metaphors for complex hardware and software interaction. By end of this session, you will understand how computer prevents data corruption when two programs try to talk to each other at once. So let's recall, let's look at the phrase race condition. Imagine a shared variable that is counter if it is 5. If a process A tries to increment it and process B tries to decrement it at the exact same time. So the result should be 5. But because of how CPUs work, that is load, modify and store. So the result could end up being a 4 or 6. So this makes confusion, right? So let's recall our discussions on semaphore. A semaphore is not just a variable; it is a synchronization tool provided by the OS. So think of it as a physical key or a signal flag. So we'll be using them in today's session. So in this session, we have four main things. One is producer consumer, then reader writers, dining philosopher, and sleeping barber. So each one represent different types of conflict. Today, our focus is entirely on producer consumer, so which is the most common problem in system architecture, right? So let's explore these things and the issues in that thing. So why classical problems? So in science, we use standard measures. In OS design, these problems are our standards. If you develop a new programming language or a new OS kernel, you must prove it can handle these scenarios. So think about your print spooler. You click print, that is producer, and the printer, it is consumer. So takes file. So if you click print 50 times, where do those files go? So they go into buffer. So this slide explains that these problems are foundation because they teach us how to manage that waiting area safely. So next, the classical synchronization problems. So when we say model shared resource usage, what do we mean? We mean we are creating a mathematical and logical framework. So whether it is a CPU cache or network socket or a disk drive, so they all follow the rules we are about to discuss. So here we use semaphore, that is low level signals. Some modern languages use monitors, that is high level objects. So we will focus on the logic that applies to both. So next thing is producer consumer problem. So let's visualize this. On one side we have a producer, it is only job is to create the data, and another side is the consumer. Its job is to take the data and process it. In between is the buffer, that is a bounded array. So imagine the buffer size has 5 slots. If a producer is 10x faster than the customer, the buffer fills up instantly. So what does the producer do? It must block. So if a consumer is faster, the buffer goes empty. So the consumer must block. So practical example is that think of YouTube video. So the producer is a server sending data over the internet. The consumer is our video player. So the buffer is that the gray bar you see when it is loading. So if your internet is fast, the buffer fills. If your internet is slow, the video passes. The consumer should wait because the buffer is empty, right? So the issues in producer consumers are a buffer overflow, buffer underflow, and it requires some synchronization. So to solve this, we need a mutex, that is binary semaphore, which will be initialized to 1. So this ensures mutual exclusion. So only one process can enter the warehouse at a time. So if a producer is putting in a box, the consumer cannot taking one out simultaneously. Next one is counting semaphore, initialized to some number, that is size of buffer. So it tracks how many empty spaces are left. And counting semaphore, when it is full, it is initialized to 0. It tracks how many items are ready to be consumed. So this execution flow would be wait operations and signal operations as we discussed before. So when producer performs wait, if it is the empty is 0, the producer stops. Then it performs wait to unlock the door. It adds the item and performs signal to unlock, and signal operation, that is full, to enter the consumer. So like that, the food is ready, like that. So if a consumer performs a wait, that is full, if full is 0, it sleeps. It locks the door with wait operations, that is mutex. Takes the item, unlock the signal with the signal of mutex, and finally the signal of empty to tell the producer, I have made some spaces for you. So what if we swapped the order? So if we called wait before wait of mutex before wait of empty, so it goes to deadlock. So the producer locks the door, finds no space, and goes to sleep while holding the key. So the consumer can never get in to make a space. So this is why synchronization is main part here. So in next video, we'll be discuss readers writers problems. Thank you.